Yeah. Today we will continue our session from pattern matching algorithms to tries. Fine. Tries is something like a tree, consisting of the characters are being represented and its leaf nodes. Fine. So each leaf in a trie will give you a string, right? Basically, the pattern matching algorithm which we have discussed before, when you are trying to identify a pattern in a very large text, but then what happens if the text is quite oftenly being rather searched, the large text itself is being searched quite often, then it's something like your text is required to be organized in such a way that wherein this text can be retrieved at a very faster rate, right? So that is what extension to this particular tries we can probably look into it. The different kind of tries, probably we start with standard tries, then compressed tries, suffix tries, and then Huffman coding tries we'll see, right? So as you have discussed, pre-processing the pattern will help us in pattern matching queries quite efficient, right? Like how in Nathmari Pratt, the last algorithm which we have seen, where the pattern which we were trying to search in the text is itself is rather required to be pre-processed before, will help us in reducing the time complexity while searching the same in that particular text. After pre-processing the pattern, the KMT's algorithm performs pattern matching in type proportional to the text size we said, right? If the text size is very large and it is immutable and search for often, quite often, like for example, the work by Shakespeare, right? Uh, Large number of people across globe will search for this kind of text, right? Written by the Shakespeare, right? In that situation, we may want to pre-process the text itself instead of the pattern. Getting it? So the text itself is quite, rather searchable. Then the text itself is required to be pre-processed. A trie is a compact data structure for representing the set of strings, such as all the words in a text. Right? So the text carrying a lot of words. So all these words are going to be here represented with the help of this particular trie. So all the leaf nodes in this particular trie will represent one word of the out of the particular text. Right. A trie supports pattern matching queries in time proportional to the pattern size. So if you look at the standard trie for a set of string S is an ordered tree such that each node but not root is labeled with a character. In root is just a root. It doesn't carry any character or label, rather, right? The children of a node are alphabetically ordered. The paths from the external nodes to the root yields the string of S. Okay, like for example, if you take a string here, S, okay, carrying bell, bear, bit, bull, buy. Let us say stock, stop. These are some of the words this particular set is having, right? Then how do you represent this particular set here with the help of this price? Root does not carry anything. Like here, bear, when you are representing bear, bear, right? You can see here B starting words with B are how many here? Bear, bell, bit, bull, buy. All these five words you can see they are starting with B. So B can be the root for all such words, and then uh, the second character, if you see E, there are two words which are having the second character as E. So E can be the internal node for this bear and bell. Fine. Similarly, second character U for bull and bike. So you can take this U as the internal node for this bull and bike. Fine. So you can see here U is another internal node. Fine for B. So if you see B here, starting with B, you can see E is one child, I is another child. For I you don't have, so I can be alone. U is having two, so E, I, and U. These are the second characters found in all these five words. Will become the child for B. Then uh, E, from E you can find these two words, bear and bell. So the child of E can be the third character of bear and bell. What is the third character of bear? A. And third character of bell is L. So A and L are the child of E. Then the there from A, after the third character A, the fourth character with the same third character, you don't have any other word apart from bear. So bear is going to be represented here. You can see here R will be taken as the child of A. So this bear, B-E-A-R, is representing one. You can see BEAR is representing one word, okay, from this particular set. And then BALL is representing another set. Then BID is representing another set, like this, okay. So you can see this is how you are representing in a tree form, right? All this set of words, fine. So the common characters from these words are being taken as internal nodes, and the leaf nodes are going to represent the word, a word of this particular set of words. So this leaf R is representing bear, this L is representing bell, and this D representing bit, and this L representing bull, and this Y representing bike. Similarly, this leaf this L representing cell. Right? This way you probably represent standard tries. Fine. A standard try uses big of n space and supports searches, insertion, deletion in big of dm, where d is the depth of the tree, rather, right? N is the total size of string in S, and m is the size of the string, and d is the size of the alphabets. Now, word match with try when you are doing. For example, if you have all these words written in a string, okay, then zero index starts with S, one index is pointing to E, and this is one word C. There is another word A. There is another word bear, like that. See a bear, cell, stock, and all. So now, after you represent these words on this particular tree, the last, as I said, leaf node represent the word. Leaf node represent the word. Okay, so this bear, bear is starting where exactly? Bear is starting at index position 6. Yes or no? At index position 6. Okay, so you will give the index value of that particular word here at this leaf, so that with the help of which you are going to notify that this particular word is available in this particular array at the index 6. That way you will index it, right? This is called word matching with a try. Then now the standard tries can be compressed. When you have only one child, you can compress it. For example, in bear, you can see here in bear, there is only one child for A, right? So you can club them. You can club them. Then you can see the leaf node carries more than one character, is AR. Similarly, bell. Similarly, bit. Right? When there is only one child, you can club them, and that is said to be compressed tries. So this standard try, this is a standard try which we have seen before, is have been compressed in this form, right? You can see this AR is compressed to AR as a leaf node, single leaf node, right? When there is a single child for any internal node, you club that internal node with the child and make it as a leaf node, right? That's how you compress the tries. Now, the compact representation. How do you represent the compressed trie? With the help of this compact representation is, you can see here, if you have these words C, bear and all, C is starting with the index value 0. This is the, uh, these are the set of strings you have. So first string is starting with 0, second is of course at 1, of course, like that. Fine. Now, let us say, for example, if this is the compressed trie you have generated for this particular tree. So these words are given, let us say. So these, with these words, when you are trying to represent this particular compressed and compact one, what do you do? Here, what is it actually? Uh, Bear. Here it is bear, right? B. B is the first character of the bear. So how do you identify it? It is in the second word. Second word, it means S of 1. It means 1, right? 1 comma, it is starting with 0 and ending at 0, 1 0 0. In the second string, S of 0 is the first string, S of 1 is the second string, S of 2 like that, right? So this B, how do you notify? This is in the second string, is the index value with 1 of set of strings with 0 0. 0 is the starting position and 0 is the ending position for the same path, right? So for example, AR you have, right? So how do you represent this AR here? You can see this AR here represented. AR is available in the second string. Second string in the set of string starts with the index value 1. 1, 2, 3 you can say. 1, 2, 3. Understand? 1, 2, 3. Similarly, for example, LL you have bell. It is bull, right? Bull is bull or bell. It is bell, right? Bell. So bell means bell is somewhere here. So bell is the ninth word. Index value is 8, and it starts with 8, 8 comma 8. You can see 8, and then the characters that you have are starting from second position, and how many characters that you have? Two characters. So 2 comma 3, right? 2 is a starting character and 3 is the last character. 2 3, right? So 8 2 3. This is how you represent the compressed type with the help of compact representation when the set of words given in the form of array of strings, right? Now coming to suffix type, uh, so when you are given a string like this, minimize, how many suffixes you have? The name itself, as I said, suffix. The condition for the suffix is required that the last character it must have. The last character of that particular string, if it is having, is to be a suffix of it. So how many suffixes that you can generate from this minimize? E, ZE, IZE, mize, imize, nimize, animize, and minimize, right? So you want to represent all of them. See, you have E is the first one, E here, right? And you can see here, you have ZE here, represented ZE. Then you have IZE, I, since you have characters being repeated in eyes and imize. So imize, eyes, and inimize, all three together can be compressed here. You can see iz, eyes, and imize and inimize. So these can be children of I, because the first character from all of them is I itself. Similarly, you can see here minimize and mize. Mize you have minimize. So both are having one two characters common at the beginning, that is mi. So taking mi as an internal, node, and it can have two childs with minimize and mice. And minimize is left alone, so minimize is one. So this is how you represent the suffix tries. Fine. So if that suffix trie has to be represented with compact representation, how do you represent it in a compact way? Index value starting with 0, 1, 2, 3, 7, you can say. So this E is at 7, starting at 7, 7, right? And this I is at 1, so 1, 1. And mice is starting at 4, right? 4 to 7, 4 to 7, like that. Okay, like that you represent on a compact one. Fine, this suffix trie. Now coming to encoding tries, and the Huffman coding, that probably is one of the widely used coding and decoding technique in many of the electronic projects, are networking projects as well. Fine. So a code here, we take probably, right, to map the characters. Fine. So I'll probably, before going for this, I'll discuss with you the prefix code. This prefix code is a binary code such that no code word is a prefix of another code word. Right. See, the condition for prefix word is a binary code such that no code word out of it is the prefix of another code word. Fine. For example, you take a tree of this kind. You have represented a tree where you have identified the leaf nodes are A, B, C, D, E. So when you traverse to left, we say 0. When you traverse to right, you say 1. So what is the code value for A? It means 0, 0, right? 0, 0, right? For B, it is 0, 1, 0, right? 0, 1, 0. 0, 1, 1, right? 1, 1, 0, and 1, 1. For D, it is 1, 0. For A, it is 1, 1, right? So you can see here this the code words given here. So you can see these code words, any of them, they are not prefixed to any other. See 0, 0, is it prefixed to any other code? No. 1, 1, is it prefixed to any other code? No. 1, 0, is it prefixed to any other code? No. 0, 1, 1, is it prefixed? No. So this is a prefix code is a one which is not code word for which is not prefixed to any other code word, rather, right? Now, coming to Huffman code algorithm, before I explain the algorithm, I'll take the example. With the help of this example, I will explain the algorithm. Okay, take the example here. The example is given as abracadabra, right? So first find out the frequencies of all these characters in this particular string. Frequency in the sense how many times each character is repeated in this particular string. A is repeated how many times? 1, 2, 3, 4, 5. So what is the frequency of 5? Of A, it is 5. Okay. Similarly, what is the frequency of B? How many times B is repeated here? 1, 2, right? So frequency is 2. For C, how many times C is repeated here? Only one. How many times D is repeated? Only one. How many times R is repeated? Two times, right? So after you calculate the frequencies of all the characters in the given string, what you do is you will find the two minimal values, right? You will remove the minimum frequency characters. That's what exactly the algorithm. I probably explain you taking the example vice versa parallelly the algorithm. So while explaining the algorithm, I'm taking the example parallelly. Okay. So you can see here in this algorithm, what is that you do is you will remove the minimum. Fine. F1. Okay, the frequency with minimum one is what C here. First minimum frequency is C, and second is D, right? So first one is identified with F1, and with which you construct a tree, that is C. C itself is going to be a tree. It means the node consists of only one, then it becomes root itself, rather, right? So There is only a single node with which you are forming a tree. That itself is root, right? C. So with the first minimum frequency out of it, you have constructed one tree, that is T1. With the second minimum frequency left over, once you identify the first minimum, you will remove from the set. Then the next minimum is nothing but D, of course, right? That you remove and then you construct a tree. So C and D, these are the two trees we have identified with minimum frequencies. Then you join these two trees, T1 and T2, you can say, right? By joining these two trees, you construct another tree, right? That is T. You will insert the same in this algorithm and you repeat this and you repeat this. This is what exactly the algorithm is, right? So here you can see C is removed with minimum frequency and D is removed, and you have constructed a tree, and you are now going to combine both of them to form another tree, CD. CD, when you have combined, their root value will be 2, right? The frequency of C is 1 and this 1, right? So you can see here, when you are constructing, the frequencies are going to be added as the root, right? See, q dot insert. While you are inserting, after you joining T1, T2 as a T, you are taking the sum of these frequencies of both these trees as the root value of T. Yes or no? So, what is the sum of these frequencies? I don't know, 2. So, 2 you have taken here, right? So for the tree that we have constructed from the two trees that you have identified with the minimum frequencies, the root value, the key value for the root is nothing but the sum of the frequencies of these two trees, right? It is nothing but 2. Similarly, after doing this, you insert back. When you insert back, what do you get now? You have A, you have B, and CD together is a tree, and R. Now again out of that you will find the minimum frequency. What is the minimum frequency you get? One is this tree and another one is R. Sorry, you get two frequent. The next two minimum frequencies that you get with B and R. So this B and R are going to be combined, and then whose whose root value when combined, the frequency value will be sum of these two frequencies, will be 4. Got it? And again insert it back. So then again you remove the next two minimum. Next two minimum, when you remove from the same, you will get 2 and 4. So combining these two, you will get 6 as the key value for this combined tree. And then when you insert back, you will get A and this 6, right? So finally you will get a tree like this, right? A and this entire tree, and whose root key value will be 11, because 5 plus 6, the sum of frequencies of these two trees when combined, you get 11, so which is nothing but the key value of that entire tree, rather, right? So your tree is going to be formed like this. Now after you form this particular tree, you are going to generate the codes. This is nothing but the prefix code. So how you are going to generate the codes? Traversing from root, when you traverse to left, you say 0. When you traverse to right, you say 1. So taking this into consideration, you generate the values for the same, right? So what is the prefix code for A? It is nothing but 0. What is the prefix code for C? It is nothing but 1, 0, 0. Got it? Understand? And for D, what is the prefix code? 1, 0, 1. And what is the prefix code for B? 1, 1, 0. What is the prefix code for R? 1, 1, 1. And this prefix code, which is generated from this particular Huffman coding algorithm, I am saying that it does not equal to any of the prefix of other code, right? That's how the encoding tries are going to be constructed with the help of this particular Huffman coding algorithm. I hope you understand this. Is there any doubt? Yes.
No, sir.